All right, yeah, let's do it. So, question for today is food production integration into homes in general. You have a third of an acre. Is it possible to feed yourself 100%? In fact, like two people?
Oh yeah.
Yes. One third acre?
Oh yeah.
Cool. How do you do that?
Fish.
Okay, but how about I'm gonna make that question more specific. Can you get that out of the net solar income that's present, not importing fish food or other things off site? That's a more stringent requirement. Is that still possible?
I believe so.
I say yes.
Yes? All right. Yeah, it's true. So how do you do it? Aquaponic greenhouse is a big part of it.
It's not on the street. Oh, they're fixing. Sorry.
Anything that's produced right now. So the sun shines, plants grow, animals live, worms worm and stuff like that. You're not importing stuff from outside that third acre. No importation from outside. The solar energy that comes in, which is the ultimate fuel, that feeds it. Can you do it? Yeah, the answer is yes. I'll show in another slide some little calculations about that. So greenhouses. We build modular greenhouses that are made of these are, for example, 4x8 and 4x16 modules. They're glazed. Modular construction. Built that in 2016. In 5 days, we also dug the ponds, put the ponds in there and did some aquaponic towers and things and seeded it with fish. So let's talk about the integration of a greenhouse as far as what all can go in there. So our basic design was, okay, fish ponds, absolutely, growing beds, growing towers. You create about 12 feet of vertical space in that case. You've got about 8 or 9 feet with towers. You got 4 feet below with fish. All of that is productive. Trees, potatoes, chicken coop, spirulina, bioreactor, like algae, vermipost, grow beds, duckweed and azolla as high productivity, strawberry troughs. We had all of that in a greenhouse. The greenhouse has been decommissioned. We haven't maintained it. Once again, it's a thing of experimentation, and then taking this to the initial experiments have shown us that, wow, it's extremely productive. When we shut down, we harvested like 200 pounds of fish, threw them in the freezer, and that was it for that experiment. We started with some polycarbonate glazing for the walls. That's Life Track 6, carrying that around. Zero marginal cost. Always ask that question. How do you build a greenhouse like this? Because this glazing is it's expensive. It's a couple of $1,000. How do you get that down to zero marginal cost?
The production of food itself.
Structure itself. Can you get that down to zero marginal cost? What's zero marginal cost? That hardly costs you. Zero marginal cost is a concept of the next unit of something that you produce costs next to nothing, like has happened with software. Can you apply that to hardware? Yes, here the answer is polycarbonate happens to be a thermoplastic. This is polycarbonate double wall glazing. Yes, that's another thermoplastic. You can 3D print it, so you can take scrap and 3D print this yourself. Zero marginal cost. This was during the build. This was the 2015 build. The 4x16 modules, all the same. So it was a 5-day workshop where we built this whole thing. That's how it looked like after the 5 days. And that came up pretty soon. Well, that didn't grow in the 5 days. That took a month or so to grow out there. But that's how it looked. That's a bunch of lettuce, arugula, and bok choy. Oh man, that stuff grows. So it's like, oh, you have more than you can ever handle. A grow bed with different crops in there, including some strawberries and onions. So let's talk about the whole food ecology in there. I'm saying that the aquaponics is one part of an integrated system, because there's of course outside stuff you can do in terms of edible landscaping and things. But with the fish, we had people The people can eat the food plants, they can eat the fish, they can eat the chicken eggs from the second part of the greenhouse. So one half focused on the growing beds and fish ponds. It turned out that worms ended up growing in the towers as well. Not sure how they got in there. It's probably somewhere they fell into the fish ponds and it got pumped up. The pumps are on the bottom of the fish ponds, but after some time we actually saw worms growing in the towers, which was cool. So you can set up dedicated grow beds, or they could just populate everywhere. The fish produce fertilizer that the plants can eat. We also had black soldier fly as a method of processing waste really quickly, where the black soldier fly larvae, they feed the fish, and you have a cyclic loop. The other part of that was chickens. We didn't put rabbits in there. You can do rabbits too. They propagate fast. Chickens, you have eggs and so forth. So once again, the worms can be fed to the fish. So if you've got vermipost beds under the chicken beds, you got a big supply of worms for the fish. And it can work like that. That was the full bloom of the greenhouse. We were propagating 10,000 nut trees, and the nut trees are part of the perennial polyculture that can be planted around the house in terms of like permaculture, various plants that are not just ornamental plants but useful plants. We had, I think, 2,000 or 3,000 gallons of water in there. We had a heat exchanger from Hydronics. You see the red stuff in the back. It was a barrel submerged underwater that we kept it. You can keep it high from high temperature in the winter from the stove, the hydronic stove. So you're just feeding hot water in there to heat the ponds as well. So we had the house heating and the fish pond heating through hydronics. That's some of the hydronic panel.
Define hydronic.
Hydronic means by means of water. And hydronic heating refers to sending hot water around in pipes. You can put that into radiators. You can put that into subfloor heating, which we had. The Seedica home, the prototype with the greenhouse, it had it all under the floor. This house right here has that. It's not connected to the stove right now, but a control panel like this makes it work. More pictures. So what you find in this, it's largely a self-propagating system. So these are just young fish that are bred. They just appear. Hey, look at that. And turn into adult fish. But we don't have to seed them. After we seeded with like 12 fish, and then sometime you had hundreds of these, and they're hiding around there. That's actually the hydronic heater under the water. The red tubing is 1/2-inch PEX that we did. And chickens provide eggs. Great. So you got some eggs and potatoes that grew. These are all from different kinds of chicken breeds that are all kinds of heirloom things. Mushrooms, we did that. That's what it was like. You take 5-gallon buckets, fill them with straw. You ferment the straw to kill off all the microbes in there. You put the mushroom spawn in there, and this happens after about a month or so. It's amazing. You poke holes. The way you do these buckets is you take regular 5-gallon buckets, poke holes in the side, and they start growing out of all those little 1/2-inch holes, just 1/2-inch holes, and they just start sprouting like that. You stack these very high, and you have a lot of vertical grow space. I'll show you the yields. Oyster mushrooms, once again, in this presentation, which is on the wiki, you can click on this. You'll see the whole procedure for how you do this, because there's some tricks in there. Like if you want to actually propagate mushrooms, the mycelium, you can actually do that through a sterile method that is open source. It's described how you can take a jar, like a mason jar, with a regular lid. You can heat that up to sterilize it. If you cut a little hole in the mason jar lid, you actually can inject with a syringe without opening this up to the environment. So you make little holes with RTV silicone, like in there. You inject it with a needle, and it's a dirty environment means to get a clean room anywhere. So you can take a look at that because you can propagate these mushrooms forever. How do you start things? So we started the lettuce and plants in perlite, just seed it. We 3D printed some net pots. This is a 3D print on a print bed. These are the grow towers. How do you do that? This is PVC pipe, a thin wall PVC. You take a, how do you do that? The whole procedure is shown. It's under grow towers. Commercial systems like this are like $100 a tower or something. It's like ridiculous. So you can take a $5 piece of PVC. You heat it with a heat. You cut it. You mark it. You cut it. You cut slits. You take a Coca-Cola bottle and ream it out, and you get a tower that looks like this. Inside it is some grow medium. This is reticulated foam. This could be anything like coco coir or other materials, or you can do like 3D print spaghetti, probably. Right? You know spaghetti? Spaghetti is a messed up print. And actually, we're getting quite excited about that as a grow medium to replace coco coir with a, how do you say coir? Is it coir or core? Coco core. Coco core? Coco core replacement. So one guy actually who signed up in an apprenticeship was a farmer in Mexico. We were talking about, okay, how do you print spaghetti that's embedded with charcoal, with biochar?
What do you print the spaghetti out of?
Plastic. It's just plastic, and the plastic is embedded with biochar. Biochar you can make from wood readily. So if you mix a bit of biochar, let's say it's 30% into the print, you've got additional grow medium for microbes, which simulates a growth medium. So in addition to the spaghetti, which gives you a structure that retains moisture, you also have got charcoal in there, biochar. So you can do this zero marginal cost. Look up G Towers on the wiki. That's really cool. You can buy these kinds of systems commercially, but they're pretty expensive, so you can do it yourself. I showed you the hillbilly heater. We also implemented that to heat the water in the ponds as well. Just a bunch of half-inch. That's just half-inch black poly, and it gets pretty hot in the summer or even in winter. It traps the heat. For watering,
the hillbilly heater, that's just a number of runs of pipe going back and forth.
Yeah.
It gets heated by the sun. Then
it's just heated by the sun.
Recirculated.
Yep, recirculated with a small pump. One of the challenges in this whole system is like why we gave up on this. So the whole experience here, it's great. Once again, startup is great. Just like the hydroponic lettuce grew 100 head, sold out in an hour at farmer's market. You know, same thing here. It's like now the lifetime design. Okay, you can do an experiment. That's fine. We'll get excited about it, and it's great. But then to get it continuous. So one of the things that happened here, we have watering of each tower through half-inch. As you see, that half-inch pipe there. It's got small emitters, and they plug up over time. It's like, okay, how do you do that? How do you solve that? Well, there's easy ways to solve that. You just have to design this a little better. But because that happened, and we had that system built already, in the summer, what would happen is that, okay, maybe a tower or two plugs up, and it wilts, starts wilting. Typically, it doesn't die in a day, but you have to unclog it every day. And after some time, more and more start clogging up. I gave up. That's what happened to it at the very end. But there's easy ways to solve it, like use a bigger nozzle. Like we had just like 1/8 inch or like 1/8 inch emitters. They definitely clog up. Well, you can go to a 1/4 or 1/2 inch. That means it's a different design. That means it would require a much bigger pump. So you just gotta have to think about how you design it. So if you do this and this works amazing, like this is worth replicating. I must say, like hands down, you'll be amazed at what this kind of system does, especially if you got fish that fertilize it for free. So you don't have to worry about.
I was going to ask about that. The water that's getting sprayed through the emitters is usually being at least partially fed by the fish tank, so there's the fertilizer and stuff like that in it. So the idea of like potentially putting an inline filter in the water system to stop the buildup in the nozzles wouldn't necessarily work. Because they need to filter it out. a lot of the stuff that you're trying to get to the plants in the first place anyways, correct?
That's correct.
Okay.
And the other part about that is, well, it's especially true. The other aspect of that is that you'd plug up those filters pretty quick because that fish water's got a lot of stuff floating in it.
Right.
Yeah, like if you stir the bottom, there's a lot of crap down there, and if you have a lot of plants, that's great. But this was like for the, we maybe had like maybe 200 pounds of fish in there. The waste built up. Like this was too much fish to feed all this stuff here. Actually, submerged pump is what did that. So the towers designs are all there 100%. Just look at the wiki. Hillbilly heaters. And I mentioned this because one way to get around those emitters that clog up is just turn on a tower at a time and use a tiny pump. So now you're getting the logic into a water circuit. And the cheapest way to do a hydraulic circuit is with washer valves. They're like $5 a channel. One of these valves is going to cost you like $10. It has 2 channels, 2 openings. You can open one, you can open up the other. So connect up an Arduino to it and a bunch of solenoid controllers, and you've got this system. So probably this would be a good solution. So using a tiny pump, because you only need to pump, they don't need constant water flow. You can just enough so the towers don't dry out. Or you can think about other means where you actually submerge the bottoms of the towers in the fish water so they would wick up. We had them just dripping, but that could definitely be another means to implement. I mean, there's so much creativity you could do here in terms of the productivity. For nut breeding, I do this slide here. We're doing some nut breeding of cutting edge hazelnut stock from Badgerset Farms, which is being developed for commercial production. Hazelnuts east of like Oregon and the West Coast, they suffer from Eastern filbert blight. So these are actually blight resistant species varieties that we have. So I plan out 10,000. Right now there's like 50. What is that? That's they got completely ripped out by rabbits and other things. We didn't protect them at that scale. You're actually hoping that enough survive, but only like about 50 survived from that whole plant out. Now that's enough to propagate them. They're starting to bear fruit and stuff like that. Perennial polyculture is what we believe in. So basically, you talk about replacing corn and soybeans as the annual kind of crop, which suffers from, what is the rate of erosion on average from an acre of farm? Does anyone know that? Like soil that washes down from every acre of farmland.
It's like 8% a year.
It's like a ton. That's like 2,000 pounds per acre of soil. Just washes down every year. Continuous. That's real right now. That's happening. Is that a case for perennial polyculture? I.e. stuff where you don't till the soil and you have zero erosion? Yeah. So nut breeding, like for example, the hazelnuts and chestnuts, we have a bunch of chestnuts here. You probably haven't seen this, but this place is full of agriculture. Like it's a whole orchard there that's got like 20 different kinds of plants. Chestnuts, hazelnuts are part of that. The chestnuts could be a replacement for the corn, which is a starch source. The hazelnuts are a replacement for the soybeans, which is a protein source. It's completely doable, but I mean, you're talking about a transition of modern agriculture into perennial, which has some challenges. I mean, that's not going to happen soon, but it's doable. It's a thing where if we get pissed, we say, no, we don't like this 2,000 pounds of soil getting washed down every year. If we are serious about that, if we're actually serious about ecological integrity, we do that tomorrow, but we're not. We accept that partly because, well, I mean, a transition plan could happen, for example, by mass replication of it. So that's why we're doing this. Okay, and then seed this all over the world. You got 10,000 of these farms, or 100. Well, the actual number is, for this project, I see 100,000 replications worldwide. That means basically the entire world. Just doing sustainable practice, that's all. So the transition, like if you talk about distributed adoption, that can happen if just a lot of people take this up. So there would have to be a lot of serious people about this. And right now, the yields are not going to be as high as corn and soybeans. But when soybeans first started, I mean, do you know the history of soybeans, for example? I mean, the yields were like tiny compared to today, like 10 times or 100 times less than today. Like right now, it's extreme, but everything starts somewhere. And for soybeans over the years, now you have extreme production, whatever, is like 4,000 pounds an acre or something for soybeans. I don't know the exact figures, but before it was like a tenth of that, you know, when they started. So anyway, it's that's happening here, right here. So we plant out all the chestnuts and, well, the hazelnuts along the key lines all over the place. Okay, so something about plants. You have to worry about nutrition too. Like that's chlorosis there, so you have to make sure the plants are getting all the nutrients. I mean, I don't know specifically why these haven't. So I just took this picture because, okay, there's some nutrient deficiencies there. That's part of the whole integrated plan. Like, how do you do this so all the nutrients are there? Integrated pest management. Pest management is I talked a little bit about that, but we basically released ladybugs to eat all the aphids. So you can see like little white flakes of aphids remaining. But yeah, they just chew through the aphids, and so you don't have the aphids. Same as we released a few of the praying mantises in there. That's on some arugula there, and you can see like all those dried bodies, dead bodies of smaller insects. These two, they self-propagated, and they just entered the greenhouse and probably did good things. But here you see some damage from I don't know what that is. That would be, what is that? What kind? What kind?
Aphids.
Aphids? Nah. Who eats up?
The ones with
Who?
hair? Looks like some caterpillars. Usually caterpillars.
I don't know exactly who this is.
Just like aphids.
Aphids suck the juice out of plants. They don't eat the plants. Yeah. So in a greenhouse now in the CDCO Home 1, which was built in 2016, so that's the second prototype. We had a water system. Oh yeah, so let's take a look at that. 800 square feet of greenhouse is what we have. If you look at the amount of area, that's about 70 kilowatts. It's about a kilowatt per square meter that comes in. 70 kilowatts is a huge amount of energy, so it's a lot of heat there. Now, plant conversion is about 1% into biomass. So from 70 kilowatts, you get 1/100th of that, so about 700 watts of edible biomass. But at any step, like if you eat those plants, so does that make sense? Like, I think it's important or like useful to look at this. You got solar power coming in. Typical figures, about 1% of that only is converted into food. So your corn, you got a kilowatt of solar per square meter. The corn is actually producing 1% or like 10 watts out of that. It's eating that up. And that's also during only the time that it grows. It doesn't grow in a winter and things like that. But the general figure is about 1%. I think the highest efficient crop is I think it's something like sugarcane, which has like 2% conversion rate. How does this compare to photovoltaics? 10x. Yeah. So it's like around 10x. In other words, if you wanted to get some service, like say you want firewood, it'd be 10x better if you got that energy from solar cells rather than growing wood, unless you got integrated polyculture and all that. Just the yields, like if you have a small area, like a quarter-acre lot, you're not going to grow lumber for fuel crop. You'll probably take it off the solar cells, which are 10 times better. But the energetics are like that here. So when we eat those plants, typical conversion is around 10%. So if you take that 700 watts that's actually being made, then you're talking about how much? 70 watts that we actually can use.
0.1%.
Yeah, 0.1% of that which comes in. Now, an average human uses about 100 watts of power. you're using like 100 watts. If you're athletic, you use more. Well, if you're exercising, but 100 watts could be a good average figure.
Is that per day, per year?
It's a rate, so it's constant, ongoing. So power is a rate, it's energy over time. So you're using that all the time. Even when you sleep, you're using like 100 watts because your brain is actually quite active.
Is that over like a 24-hour period though?
Yeah.
Okay, so 100 watts a day.
100 watts times 24 hours is 2.4 kilowatt hours. So it's like, once again, rate is energy over time. But yeah, 24 hours of that means you're using like 2.4 kilowatt hours in the food that you eat.
I heard humans consume as much as 13 elephants in terms of their metabolism.
For how long and over
Or
what
just-
time?
Just all of the stuff they do throughout the day normally. And it's
No, but are you talking over a life?
No, just as
like-
wattage.
Oh, it's wattage.
Yes.
Well, yeah, because and what is that? It's the average home uses a kilowatt, but all the industrial system, I think, is it's actually like 2 or 3 times more than that. So an average Western human constantly uses about 2 kilowatts, 2 or 3. I think it's like 3 kilowatts, let's say. Is it so you're saying it's as much as a few elephants?
13 elephants.
As much as 13 elephants. Okay.
Yeah, a book called Scale about the wattage of animals where they consume a mouse, a human, and,
Yeah.
you know, and it's
Yeah.
on a scale.
Yeah. There you go. So in this kind of just basic consideration here, you're close to actually getting the food that you need, but you have to divide. You've got sun only a partial time in the day, so it's not just from the greenhouse itself receiving all that energy. You can't feed yourself, but if you give fish food to the fish, they grow fast, and yes, you can, because the production rate is like 2 or 3 pounds per day of fish in the system that we have there. Well, what if you use, so this goes back to the question I asked, it's that half acre or third acre. If you look at the amount of energy that comes into that, if you are growing grass, like say to feed rabbits, or you somehow otherwise generating food not present from the sun. So we're not talking about like taking a tree and like converting it to, say, like a bunch of worms end up eating that tree and you convert it into worm biomass. No, that's stored energy over years. I'm saying that present energy. About 1/3 acre actually gets you that present energy, like say like grass or whatever, for a rabbit. So yeah, the short answer is yes, like the actual energetics could let you do that. So that's cool. With zero external inputs. Therefore, it's useful to think about edible landscape, aquaponic greenhouse, things like that. But look at this low stocking rate. 300 pounds of fish mass in 3,000 gallons of pond. That's about what we had. They grow 1% a day, so that's 3 pounds of fish per day. That is true. See the tilapia page. That's a full diet, but you have to feed the fish with something. If you grow, like, say you integrate that with your human waste in the biodigester or vermicomposting of all kinds of biomass, yeah, you could probably do that. Just generate all that food for the fish. Mushroom meals, look, oh, this is crazy, actually. So you gain about 1 pound of wet mushroom weight per 1 pound of dry straw. So this is in your buckets. Our results, and you can actually click on that and collected some data. We got 12 pounds of mushrooms from 5 buckets over November 10 to February 18. This was back in 2016. They're 30% protein. 12 pounds per square foot is not bad. It means, 12 pounds from that tower. Pretty cool. Duckweed. We never did the full troughs of duckweed. We did a little bit, but along the back wall, how about you put a bunch of gutters, 10 rows, 30 feet long. Like, this is, say, the back wall. Just a bunch of gutters. where you have water trickling from one to the next, and you've got duckweed or azolla. Azolla is another plant like duckweed. It's rich in nutrients that the fish can eat. So the harvest rate is like, bottom line, 1 kilogram of harvest per day. Per day. That's good. That would get you, if the conversion rate by fish is, it's not going to be as, well, assume the case of, once again, 10% for any trophic level, like anytime some critter eats something else, let's say you extract, say, 10%. But if you got, yeah, I can't tell you exactly how much you can feed, but I mean, 1 kilogram of duckweed per day, that'll get you some fish growth too.
So
Are
you saying that roughly 10 pounds of duckweed could turn into roughly 1 pound of fish?
Yeah, so 10%. Yeah. So that's that. And then if you do that, you'd have to think about if you want it to be self-harvesting, I have to think about the system that would allow that to. So basically, like you flow enough water in there that only part of the duckweed is drained downstream. So you have timers and things like that. That's something to figure out. We never got that far. So closing loop, duckweed and gutters, redworms. I mean, redworms process all kinds of waste really quickly. So redworms are like earthworms, but they're more good on waste, including human waste. Grass and hay from the outside. What about an outdoor pond in the summer? Yeah, you could integrate that as well. Algae bioreactor. So 30 minutes. Let's just talk about a couple of ways to automate. I mentioned this. This is actually FarmBot, so it's a open source kind of. It is an open source project. So think of this as seeding your sprays. Just starting the plants automatically, so you can take that out of the equation. You just plant them in towers. So you put them in, you plant them in the little net pots, and then you just put them into the tower. So say, you can do a few of these a day, which doesn't take you any time. So there's a little bit of automation that can happen. Fish feeders, you can automate that easily. For chickens, you want them. Well, if you have them open to the outside, you want them to come in. If you have them going outside, we had a little pen for them. You need a door, an automated door, so you don't have to, oh, did I forget to lock up my chickens? Because all the critters love to eat chickens, and your chickens disappear very quickly. So came to factory farm with 100 chickens, and then over like 2 or 3 years, that went down to like 5. So they just get, they get eaten up. We had them free ranging. So I mean, a free range chicken is a dead chicken unless you prevent that.
Yeah.
Unless you have means to address that in a rigorous way.
Were you incubating and hatching chickens?
Yes, we were.
A few years ago?
So the first year, before coming here, just incubated them in an open source incubator, of course. Grew them out, literally had 100 chickens, came here with a Suburban, 100 chickens and some power tools and the tractor that broke, and started the operation. But yeah, so automation is cool, like chicken incubators. Yeah, so you can take a few of the eggs, just have your chickens propagate. I mean, you can design an operation that you accept that if you want a free range, accept that, but just keep breeding new chickens on an ongoing basis because they're going to disappear. Sprout machines, chicken incubators, window opening, and the greenhouse is important. Yeah, so in any case, the thing I didn't mention about, I mean, the whole perennial plantings around the house, I mean, you can grow so many things. Your peaches, like here we have tons of peaches, Asian pears, apples, pears and plums, the nut crops, all kinds of other edibles. I mean, you can really deck out your garden with a lot of stuff. And we want to make that a standard feature. So you basically get this whole food garden. You've got all kinds of nuts that you can pick. I mean, the chestnut trees, they're extremely productive. So you can do things like chestnut bread or whatever. They're good. They're actually quite tasty, so you can have a full meal out of them. But I mean, if you deck your third acre, the average size of a home, with all this edible landscape, you're largely self-sufficient. For example, like I mentioned, if you go
if you want to feed the fish with grass, I showed that there. But if you do things like, okay, a big nut tree, that's going to provide you so much food that that third acre is completely 100% able to give you your diet. And I'll leave it at that. It's a great thing to do. Yeah. Any questions or that we can save? No, I think I'll quit here. But that was our experience so far, and we're gonna make this as like the aquaponic greenhouse as well as the edible landscaping a standard feature in what we offer in the house builds too. So we don't have that yet, but we will. Go ahead.
So you're growing mushrooms in there. Like mushrooms grow really quick and stuff.
Yeah.
You already have protein from like the fish. Sounds like you have more protein than you need.
Yeah.
And then a little bit from eggs.
Yeah.
Are you growing them mainly for protein diversity, or also your mushrooms have a lot of like vitamins in them?
It's more about diversity. I mean, I got tired of eating them. Eggs and with mushrooms really tasty. Maybe for the first 3 days. Then you get really tired of them. Yeah. So think about, okay, if you're not going to do the mushrooms, think about 100 other crops. But now you're talking about managing a whole complex system. So this is much harder than your standard monocropping, because that means you have to have 100 times more information to work with. It's harder.
And then were you giving the chickens chicken feed, or were you just like throwing all the stems and stuff in?
We're typically, I mean, we gave them a lot of the worms, of food waste. Yeah, we did give them some chicken feed, but when we had them free ranging, no, we didn't feed them at all.
I've got a friend that built a frame and put chicken wire over it.
Mhm.
Big, it was 20 feet, and he had jacks on wheels, and he
Yeah.
just move it, and he didn't have to worry about predators.
Yeah, exactly. And for that, if you have that on a scalable fashion, solar hydraulics, like the solar power cube thing, slow moving solar energy. So you only get so much energy from a solar panel, but a single panel can move a tractor, chicken tractor like that, about 1,000 feet per day. And that requires photovoltaics and hydraulics. So you're using the photovoltaics to run a very small motor, which turns a hydraulic pump, which pumps at super high pressure. So a tiny hydraulic motor can move like 1,000 pounds. And that way you have basically slow moving photovoltaic machines that are automated, and I don't have to worry about it. It just moves it a little bit every day. So if you think about transition of agriculture to solar with automation, you can do that completely. So think about tractors, like say you got harvest, unattended, you have a whole bunch of panels, like a whole load of them for a big tractor, like the replacement of those standard 400 horsepower John Deeres. You just put a whole array of PV on top, and it will go like super slow that you can hardly see it, but over a day it adds up. So you can have that kind of thing. I do think there's a lot of potential for it. Like, for example, a shredder is a great example. You have a small panel on top connected to a hydraulic motor that turns something that can chew up steel, even from one single panel. It moves super slow, but the force it has is incredible, right? That's the power of hydraulics, and integrated with solar, that could be a viable option for much more of industrial agriculture. We'd like to do much more of that. We know that the hydraulics work. For example, we call it the power cube, small power cube, hydraulic power unit, small motor, hydraulic pump that drove the whole tractor, a thing like this. It's an engine for the tractor. Now, it didn't move fast. It moved very slow, kind of like that, but it's a 5,000 pound tractor, right? And that was running on 100 watts, 100 watts, 1/10 of a kilowatt. Yeah, so hydraulics are powerful. That's a good technology. And
His kids moved it. Kids moved it every 3 days.
yeah, and if you have an integrated operation, you get too many of these details. So yeah, automation can help if it's appropriate open source automation. Yeah, at zero marginal cost. Yep.
You've talked about biochar, and I've seen that in the wiki and stuff.
Yeah.
Can you talk about what that is for? And what
Yeah.
uses are?
Biochar is, so if you partial combustion of wood, you burn wood, but you don't let it burn out all the way to ash. You burn out all the lighter elements, and what stays behind is pure carbon. So you basically you can take, for example, a 55-gallon drum, throw a bunch of wood in it, light it on fire, close the lid, and a day later you have a bunch of unburned charcoal in there. We used it. Well, you can use that for soil amendment. We actually ran a power cube on that. So we took one of our standard engines, we put a gasifier burner on that, meaning you're now burning that. You light that charcoal from the bottom, it emits gas because it's oxygen starved, so it doesn't burn fully, it just decomposes into carbon monoxide and hydrogen.
So it's just another name for charcoal, pretty much.
Yeah, charcoal, but biochar would be activated charcoal. How do they do that? How do they turn regular charcoal into activated charcoal?
Well, I don't know the answer to that, but I do have something to say about biochar and using biochar. It's really smart to soak it in water and fertilizer and like fish emulsion and stuff to soak it up with nutrients so that it doesn't actually, it might leach nutrients from the soil. So if you put it in the soil to amend the soil, you actually can hurt the soil if it's not already charged with nutrients. So you soak it in drums for like a week in like fertilizer, fish emulsion, and water, and then it's ready to go. Just wanted to make that.
Yeah, so biochar is basically like a big sponge where all kinds of microbes and nutrients can live in there. It's because you want air for plants and for biological life. It has a lot of airspace.
It's like habitat for microorganisms.
Yep.
But then, so how do you activate? Or what's
How you do it?
Activate.
I don't know.
Heat.
How do you do it?
Oh, activate.
With heat, oxygen, and certain chemicals.
I throw it in the pond. You can
I-
just put it in a sack, throw it in a pond.
And that activates it?
For a
Yeah.
week, yeah.
Go ahead.
So, how much percent of the plastic did you say you were putting biochar in? You say like.
So if you do 3D printing filament, you can probably put in about 30% biochar into that 3D printing
Wouldn't that
filament.
weaken the plastic a lot?
Yes.
Like especially after it goes away.
Yeah, it does. So that's why there's a limit.
Okay.
It's acceptable. You can still print with it, make structures with it at about 30% higher, and you kind of starts collapsing.
And then, do you think? So, are you putting it in there to give the organisms like little air pocket or
Yeah,
like little structure areas?
yeah, exactly. So microbes and all kinds of biological activity can thrive in there because on plain plastic, it doesn't have all that porosity. The plain
then-
plastic itself, only the spaces between the plastic have that space, that air space.
The little hydroponics kits I were making, I spray painted like 95% of it black and just left a little strip with the tape so I could see the water level in order to stop plant growth. Because if you left it without light protection, then it would actually grow algae.
Yeah, you can get too much algae in there. So you can say that in the case of tilapia, that'll be great because they love algae. They clean your tank. In hydroponics, yeah, you can't. The algae eat up all your nutrients. Mark?
How is your system with you're using that tryptophan
The double pane polycarbonate, yeah.
It's 3 layers of poly, right? With
Yeah, 3 layers, so it's 2. Well, actually, no, this one is the cheap stuff. It's just got 1 cavity.
Oh,
1 cavity.
how was it in the winter? Did you guys try running it in the winter with the fish? And all
Yeah, I mean, we ran it year round, and without heat, the pond never freezes. But that would kill off the fish, so we heat it.
Yeah.
After we took the fish out, I mean, that never freezes in the winter. So it is good. Now you're also tapping to the heat 4 feet under the ground too. So that cool actually heats the water. Now what's cool about 3D printing? Print yourself like 8-wall polycarbonate glazing, right? So think about stuff that lets air through, lets light through, but it's highly insulating. That's That's the beauty of 3D printing. You can get these complex geometries that can do useful things. That would be that's a great application, like, because or like honeycomb cell-like structures that physically are impossible to extrude. You can't get that through a standard extruder, but in 3D printing, you are able to print whatever you like. It's not limited by the kinds of constraints that an extruder, which basically does a whole parallel thing. It cannot put like a cell next to a cell next to a cell. It can produce like a straight hole. You can have multiple layers, like multi-wall glazing, but you can't get as complex as a 3D printer. Mm-hmm.
What's you talked about pests and stuff, like,
Yeah.
how much maintenance would it be for the greenhouse that you showed before, like weekly, daily?
I don't have a good answer for that because it depends on everything. So that means, oh no. But I think in a highly integrated system, I mean, it pretty much set up the right biology in there and it will take care of itself. Just like the question would be, okay, outside in the real world, you got a lot of land or whatever, you're growing stuff. How much do you maintain it? Well, in principle, the whole ecology of the whole system should maintain itself. The limit of this aquaponic greenhouse is zero maintenance. It all takes care of itself. That would be like 10 PhDs, whatever. Or that's a complex. You're designing a complex engineered system, and that's living machines come to mind on that. Living machines are biological wastewater treatment plants that include all kinds of different critters in there, from plants to mollusks to insects to amphibians and all that. That's a commercially available wastewater treatment system. It's also super expensive and closed source. So, you contact the guy and they won't tell you what they're doing. But once again, if we develop that in the open source, a highly robust system, you build the robustness into it by how much attention you put into the understanding the whole system. This is complex systems design. Yeah. But the limit would be it's completely manageable, like a few minutes a day. You're just going in there to harvest stuff and check up on it. That would be the deal. And it's completely possible, but you got to have that design that does that and put in all the different elements that are in there. Yeah.
I have two questions. One, how much do you think your system approximately costed to build?
About $5,000 for that greenhouse.
That's not bad.
Mm-hmm.
And then in the house design, I noticed how the underwater lake system thing, or the lake system thing for the house thing you were showing us, was underground.
The ponds?
Yeah, the pond thing.
Yeah.
But it was like underneath the house. Was that in order to make sure that it's low enough that it will never freeze and you won't need to worry about getting it or anything? Just the ground will insulate it and the ground will never freeze around it?
It was more to save space, because if we went up, we're losing those number of feet of growing space. So I mentioned the figure of about 12 feet. Instead of having 8 feet, we got 12 feet of biological activity. So it was to optimize space. And then with the earth, that also serves as your container. We stabilize the sides using treated plywood and then insulation and a liner. But yeah, that was to maximize space. The idea there is like a super intensively grown thing in a small space that you can put anywhere, like any lot, any house can do that. That was the idea, to really compact it down in size. Mm-hmm.
Have you ever heard of this cubic farming thing that's rotating with the LED lights?
No, haven't. But I think about the LEDs because now solar energy is literally at zero marginal cost. I think it's worthwhile because you can multiply your yields if you have access. So you got solar photovoltaics running your LED lights to just get more productivity out of the same space. And that's pretty efficient because LEDs are, what's the efficiency of an LED light? Like how many percent? So you're getting a high fraction of the energy.
That's my job. I'm working in a light shop.
Okay.
Manufactures LED and they get more and more efficient.
What is that efficiency right now?
I don't know, but if they get 10% more efficiency, it's a big deal in the lighting industry. And so we're constantly innovating and upgrading, and throwing away last year's stuff to get the new stuff.
Yeah. Right. So it would be a good idea, like in a cold, say you got to grow in the winter, insulation is a big part. So you could even do you've got solar photovoltaics and you're actually doing the fake light with the LEDs, but there could be a good use case for that if there's any sun and you're in an extreme environment.
So they're doing that with marijuana. Right.
Mm-hmm. Yeah.
Any last questions?
Any last questions?
Anybody know how to get rid of squash bugs?
Yeah, they're
Squash
saying.
them.